This is part 5 of a lecture on statistical inference. As we have learned, statistical tests for linear regression are based on probability distributions such as the t-distribution and f-distribution of some test statistics. Probability distributions of the test statistics were derived from a set of 4 mathematical assumptions about the distribution of residuals. In this section, we study those assumptions and diagnostics for checking if the distribution of estimated residuals deviates from the assumed patterns. The term at the end of the regression model, epsilon, or residual, is the difference between the observed and predicted values of the dependent variable. It is assumed to have random variations. This is a 3-dimensional graph, and the plane at the bottom is y by y hat. The diagonal line indicates y equals y hat. This graph shows the assumed pattern of distribution of epsilon for 5 different values of y hat. 3 of the 4 assumptions about the distribution of residual are illustrated here. Have you found them out? First, all of the 5 distributions are symmetric and bell-shaped, showing that residuals are normally distributed. Second, all of the curves look equally widely spread. It is possible that some distributions are widely spread and others are narrowly concentrated. But here, it is assumed that the dispersion of every distribution is the same, i.e., the variance of the normally distributed residuals is the same at every point of y hat. This may be called the assumption of equal variances, or constancy of variance. In statistics, it is called homoscedasticity, and if the variance varies, it is called heteroscedasticity. Third, the center of each of the 5 distribution curves appears to be exactly on the straight line representing y equals y hat. It is possible that centers of some distribution curves are above the straight line and those of other distribution curves are below the straight line, but it is assumed that the center of distribution is always exactly on the line. This assumption is called linearity. This slide mathematically summarizes the 4 assumptions. The first 3 were illustrated in the previous slide, though in a different order from this list. It is difficult to visually express the last assumption, independence among residuals. By the way, the first assumption is called linearity, but we should be careful when we use the word linearity, because in statistics, linearity means different things in different contexts. As we studied, epsilon is the true residual, and E is its estimate. We will never see the exact distribution of epsilon, unless we have an infinitely large number of observations, but we can examine the distribution of its estimate, E, for observed cases, because the distribution of E should be pretty much like the distribution of epsilon. Mathematicians have shown that, if all of those 4 assumptions hold true, then the test statistic, T, asymptotically follows the T distribution, and the test statistic, F, asymptotically follows the F distribution. So, if the distribution of epsilon departs considerably from those assumptions, p-values and confidence intervals that we got on the basis of those distributions may not be accurate. So we look at the distribution of E from regression analysis, and examine if its pattern appears to be compatible with the assumptions. This examination is called regression diagnostics, or linear regression diagnostics. The distribution of E is not exactly the distribution of epsilon, but we expect that the distribution of E looks like the true distribution of epsilon, particularly if the number of observations is large. Let's look at a few examples of linear regression diagnostics. This histogram summarizes the frequency distribution of residuals from some regression analysis. The curve is normal distribution fitted to the histogram. So the frequency distribution of residuals looks fairly close to normal. Note that this graph shows the entire distribution of residuals from the regression analysis, including all cases with different values of y hat. But the assumption is that residuals are normally distributed among cases that have the same value of y hat. That cannot be examined unless we have a very huge sample. Still, this graphic examination is an important tool of regression diagnostics, because, if residuals follow the same normal distribution at each of different values of y hat, then residuals pooled together over different values of y hat should be normally distributed as well, and this graph seems to meet the expectation. But the distribution of estimated residuals could be far from normal, as shown in this artificial example. The distribution looks to be strongly skewed to the right. Let's look at another type of graph for regression diagnostics. This is a plot of residuals against y hat. This graph seems to suggest that the distribution of estimated residuals is compatible with the assumption of equal variance and the assumption of linearity. The extent to which the points are vertically scattered appears to be about the same, whether the points are in the left section of the graph, or in the middle section, or in the right section, i.e., regardless of the value of y hat. This means the pattern is fairly consistent with the assumption of equal variance. Also, the vertical spread of points appears to be always centered around 0, which is consistent with the assumption of linearity. But this pattern seems to deviate from the assumption of equal variance. The vertical spread looks to be greater in the right half of the graph than in the left side. That is, the variance of residuals is not constant but tends to be greater for higher values of y hat. By the way, in regression diagnostics, in addition to original values of estimated residuals, studentized residuals are used sometimes. Original residuals are used in the left panel, and studentized residuals are used in the right panel. The patterns are the same, but the scales of the vertical axes are different. The studentized residual is the original residual divided by the estimate of its standard deviation. Not only it is used for regression diagnostics, but also it is useful for identifying outliers. This slide shows an artificially generated distribution of residuals. The left panel is a plot of y against y hat, and the right panel is a plot of residuals against y hat. In the left panel, points do not appear to be scattered around the straight line of y equals y hat, but around some curve. The right panel shows that residuals tend to be negative near the low and high ends of y hat, but positive in the middle, not always centered about 0. This pattern suggests a noticeable violation of the linearity assumption. There are a few things about the diagnostics that should be kept in mind. First, the diagnostics is not a direct examination of the assumptions. In the diagnostics, we look at the distribution of estimated residuals in the sample, but the assumptions are about the distribution of true residuals, which we can never look at. Second, some students may do some diagnostics, find significant departures from the assumptions, and conclude that, now the results of regression analysis should be thrown away. This is a mixed up of estimation and statistical inference, which should not be confused with each other. OLS is a well-designed method for estimating parameters of linear regression models, and OLS is not based on the assumptions. But the standard procedure for computing p-values and confidence intervals is based on the assumptions. Considerable deviations from the assumptions do not necessarily make you skeptical about the estimated parameter values, but may make their p-values and confidence intervals questionable. Third, we should not confuse distribution of residuals with distributions of y and x's. Some students may look at distributions of the dependent and independent variables, find that some of them are far from normal, and then conclude that the regression analysis was invalid. But that is wrong. What we studied is assumptions about distribution of residuals, not about distributions of values of y and x's. In addition, we should keep in mind that the assumptions do not have to hold exactly true. Probably, it is rare for those assumptions to be exactly true in the real world. For example, probably nothing in the real world is precisely normally distributed. So, p-values and confidence intervals that were obtained from linear regression analyses may not be exactly correct. But, if departures from the assumptions are not considerable, p-values and confidence intervals may be accurate enough and still useful to us.